All right, let's get started on this problem here. The setup is we have a copper rod. We're given length L of the copper rod. So I'm going to go ahead and draw that into our picture. Lying on a frictionless table. So this is actually a top view diagram here. And that's because we don't want to have to worry about the weight of the copper rod. So assume that we're looking at this top down. It's lying on a frictionless table. Each end of the rod is attached to a fixed wire by an unstretched spring. So we've got some springs in play here, and we're told that the spring constant of these springs is K prime. So they both have spring constant K prime. Magnetic field B prime is oriented perpendicular to the surface of the table, and we can see from the diagram that it's coming out of the page. All right. So first question is, what must be the direction of the current in the copper rod that causes the springs to stretch? So to answer part A here, you need to use right-hand rule. So whatever your version of right-hand rule that you use here. So for me, it would be fingers in the direction of current, and then fingers bend in the direction of B field. So I cross B, right? And if I do that in this case, I going from left to right, B coming out of the page, then I get a force as to be downward. So my force is actually downward. So it's going to extend the springs. Okay, good to know. Now moving on to question B. So always, whenever you're doing these B field problems or these force problems, currents or particles in B field, always pause and connect to the direction first. What that does is it gets your brain in the mindset where you're physically into the problem a little bit more. If you do the calculation first and then worry about the direction afterward, then you're doing the math and stuff, and you might be sort of conceptually involved, but not as much as if you did the direction first, especially when you do right hand rule. So just the act of doing right hand rule, and that is making a three-dimensional motion with our bodies while thinking about the problem, that actually activates places in your brain for spatial thinking. So sometimes students are like, oh, I do right hand rule in my head. And I just say, well, you're cheating yourself then, because our brains are part of our bodies and we exist in this three-dimensional space. So really, it's best for your own learning if every time you apply right hand rule, your hand moves. Okay. Part B, if a current I prime moves through the rod, by how much does each spring stretch? Cool. So now we're given the current here. Let's see. So right hand rule, the force is going to be down. Oh, here, I'm sorry. A is asking us what must be the direction of the current. I was like, why don't I have that written down? So if the springs are going to extend here, so I answered this question in a funny way. If the springs are going to extend, then that means force is downward, and that must mean that my current, I'll call it I prime, has to go to the right by right-hand rule. A leftward current would cause an upward force, and I mean upward in the plane of the page, right? So that the springs would compress. So the springs extend in this case. Okay, sorry, moving on to B. If a current I prime moves through the rod, by how much does each spring stretch? Cool. We know this. We know about Hooke's law and that kind of thing. Let's remind that the equation that we're looking at here, the force that the B field exerts is equal to L I prime here cross B prime. Okay, so this is a vector product. These are vectors. Notice they have hats. It matters. So when you're dealing with vector products, be sure that you're using vector notation. A vector is different from its magnitude, right? It's a different quantity. A magnitude of vector describes only part of that quantity. So if you're talking about a vector, then, and you have to be, or else you can't be doing a cross product here, then please use appropriate notation. Now, if I'm going to, what I can do here is say, all right, I'm going to figure out the magnitude. So now I'm leaving the hat off. The magnitude here is then going to be L I prime B prime times the sine of the angle between them. Now in this case, I is in the plane of the page, B is in and out of the page. So we have a really clear-cut case. In this case, phi is equal to 90 degrees, right? And if phi is equal to 90 degrees, then sine of phi is equal to 1. So that's cool. So we have that, and that allows us to simplify further. The magnitude of the force is equal to L times I prime times B prime. Okay. Oh, I shouldn't have put this hat over my eye here. Let me just get rid of this hat. Okay. L I prime. Cool, because that's all magnitude, right? Multiplied by each other. All right, so now we have a magnitude of the force. Now, what we know from Hooke's law is that the spring force magnitude is equal to K prime times X, whatever the extension is. And actually that's what we're looking for, right? We're looking for that. How much does each spring stretch? And right now there's students that are like, oh my gosh, why didn't Stephanie put the negative sign in Hooke's law? So I am just caring about magnitude right here. Yeah. So I know what the directions are, and the reason, remember, that that negative sign is in Hooke's law is because it's there to remind us that the displacement and the force are always in opposite directions when it comes to spring force, because that's true for any restoring force. That was Physics 221 content. So right now I don't have hats on here. Negative sign's not there. I'm working with the magnitude. So we have two springs, right? This matters. We have one rod and two springs. So that tells me that the spring force is going to be doubled, right? That's equal to the magnetic force. Those magnitudes are going to be equal. So I can say 2k prime x is equal to my magnitude of my magnetic force, which is L I prime B prime. And then I simply solve for x there, and I'm able to express x as L I prime B prime over 2 k prime. And then pause for a moment and ask yourself, does this make sense? So does it make sense if there would be more extension if there was more current? Sure, more current would mean more force. Does it make sense if there would be more extension if the B field was greater? Sure. B field is greater, again, that force increases, so your extension would increase. And then notice the K primes in the denominator. So if if the spring were a stiffer spring, does it make sense that there would be less extension? Yes, it does. So all of that, when you come up with a symbolic expression, kind of run it through your common sense filter. Does this make sense that these proportions would end up this way? These things in the numerator, these things in the denominator. And in this case, it does.